Hello, I'm Dan Klingman with the Lincoln Electric Weld School, and we just got done making several different welds, some lap joints, some T-joints, and some fillet welds, and also some groove welds. Now we finished those welds, but how do we now determine where do we need improvement at, and how do we determine whether those welds are acceptable? There's a couple general criteria that we can use to look at the welds and determine where we need to improve at. There's a lot of different types of what we call non-destructive testing, where you can still test the part, but it can then still be put into service. One of the most common types of non-destructive testing is the visual inspection. So when we look at visual inspection, we're going to take a particular joint, and we'll use this T-joint here to start with, and we're going to look at it, and there's a couple different parts of the weld that we should be familiar with. On this particular weld, we've got a toe of our weld here and a toe of our weld here. The part across the middle is what we refer to as the face of the weld. So when we look at this particular one and we want a flat face, you want that area from here to here to be relatively flat. The alternative would be to have a concave weld. Concave welds can be more susceptible to cracking than, say, a flat or even a convex weld, which would be slightly humped up in the middle. So we're looking for a flat face as the key. The other criteria that we're going to look at is proper placement in the joint. You know, obviously we want the weld to be in the joint. We don't want to be straying out of the joint. And I've got an example here of a lap joint, and we've got a fillet weld on here. And if you look right at the beginning, it's actually more on the bottom plate than the top plate. That's what we're referring to as proper placement. So you can see as we started the weld, we noticed we were on the bottom and then came back into the joint and proceeded down the weld. So again, making sure the weld is where you want it and it's properly placed is also a key criteria to look for in your welds. The other one is what we call, you're looking for the weld to be fairly uniform. And by fairly uniform, we mean nice and straight, and also, you know, you don't have places where it's wide and narrow, wide and narrow. So for example, we built the pad earlier, or when you build a pad, the idea behind that is to get consistent with, number one, keeping a straight line, and number two, making sure that they're consistent in width as you proceed down the pad. So a fairly uniform weld is also an important criteria to look for when welding. And one of the last ones that we look at is the wash-in, and we'll select this one here. This is a lap joint, but when we refer to wash-in, if we go back and we look at the toes of the weld that we talked about, we want the transition at the toe of the welds to blend in smoothly with the base material. What happens is if it doesn't transition smoothly or have good wash-in, you could possibly get a stress riser there. And one of the examples that we commonly use for a stress riser to simulate this would be if you take a piece of string and you pull on it and it's hard to break. Well, if you go and you put a knot into it, like for a fishing line or something, and you then pull on it, you'll notice that fishing line a lot of times will break right there where that stress riser was. Same thing in our weld here. We want it to transition smooth and have a nice wash-in with our base material in these particular areas at the toes. So as a summary, just to wrap up here what we've talked about, there's 4 general areas that we can focus on for visually inspecting a weld. One of them would be a flat face. One of them would be proper placement in the joint. One is fairly uniform, being the weld consistently shaped down the joint. And the last one is good wash-in at the toes of the weld. So if you're looking for any other information on welding, you can visit lincolnelectric.com.
clean the material using cleaner. Then spray it. Then wipe it using cloth. Then we wait for 3 minutes until it dries. After it dries, we apply the penetrant. Okay. We spray it in the straight lines. And then let it dry for 10 minutes. After it dries, we clean the penetrant using cleaner. But you must clean using cloth. You must clean it until it cleans. Then we apply developer.
Non-destructive testing, magnetic particle inspection. The magnetic particle examination is an excellent method to investigate near-surface defects in ferromagnetic materials. This video shows the basic principle and the practical procedure. The material tester gets the machine ready for use and inserts the test piece between the two poles of an electromagnet. Then she takes a bottle with a suspension of magnetic particles, turns on the electromagnet with a foot switch and applies the suspension of magnetic particles onto the test piece. Already in daylight, dark lines are visible on the surface. The lines can be seen much better under ultraviolet light and particularly well at darkening the daylight. The suspension contains pigments that cover the magnetic particles and fluoresce under ultraviolet light. The particles run off in areas free from defects and they are attracted and clustered near defects. This workpiece shows a whole array of cracks. The basic principle is to magnetize a ferromagnetic workpiece parallel to its surface, as shown in the sectional view. If the workpiece is free from defects, the magnetic field lines run within the workpiece and parallel to its surface. In places of magnetic inhomogeneity, for instance near cracks, the magnetic field lines will locally leave the surface and a leakage field occurs. Now, if a suspension of ferromagnetic particles is applied onto the test piece surface, the magnetic particles will run off at defect-free areas. In places of leakage fields, the magnetic particles are attracted and clustered together, thus indicating the place of the defect. The method works best using a pigment which covers the magnetic particles and shows fluorescence under ultraviolet light. Even cracks can be detected that are not open to the surface but just below it, as long as they are not too far below the surface. But one precondition must always be fulfilled. the magnetic field lines must be perpendicular, or at least at a certain angle to the defect. Otherwise, there will be no leakage field and the defects remain undetected. Our test sample has been magnetized in horizontal direction. The magnetic field lines run horizontally. This is the reason why cracks in vertical direction are visible particularly well. To make sure to detect all near-surface cracks, one has to magnetize the sample once more and best perpendicularly to the first time. To do this, the material tester switches the machine over to the current flow method. A high electric current flows through the sample, generating a circular magnetic field. Now the cracks in horizontal direction can be seen very well. The tested sample is a hardened sliding guide. The cracks have been formed during the hardening process and the subsequent grinding operation. Still another test piece has to face the magnetic particle inspection, a section of a large gear wheel. The same procedure again. Placing the gear wheel between the magnetic pole pieces, magnetizing and applying magnetic particle suspension. Already in daylight, there are indications of cracks, and again, they are best visible under ultraviolet light while darkening the daylight. The visible cracks are so-called fatigue cracks. They have been generated during the operation of the gear drive due to a mismatch of the gear wheels.
This is a demonstration of eddy currents. I have here a piece of aluminum suspended on a pendulum arm, and I have a powerful magnet, permanent magnet down here. It produces a magnetic field in this direction, and when this piece of aluminum enters that strong magnetic field region between the two poles of the magnet, the change in the flux, the magnetic flux, through this piece of aluminum induces an EMF in the aluminum and currents in the aluminum. And the direction of those can be determined by Lenz's law. If the magnetic field is in this direction, as the aluminum enters the magnetic field region, the magnetic flux is increasing. It's increasing in this direction. To oppose that increase, there are currents that go in this way that produce an induced magnetic field in the direction opposite the original magnetic field. And that works out, those actual currents produce a force that opposes the actual motion of this aluminum plate. So what you'd be looking for is to see that whereas normally this would have oscillated without much friction for a long time, when allowed to pass through the magnetic field, the force is quickly, or the motion is quickly damped out. Center that a little bit better. That's called eddy braking. It's used a lot in amusement park rides, actually, to slow down amusement park cars in roller coasters, etc. Now with this piece of aluminum, we've got slits cut into it. So those circular eddy currents are not, this will prevent any eddy currents to be produced. So this one can oscillate for quite a good long time and be very happy. The other thing to mention about this one, the solid piece of aluminum, is that not only do you get braking as it enters the magnetic field and as the magnetic flux is increasing through it, but you also get braking as it exits the region of the magnetic field. And you get currents in the opposite direction. Both when entering and exiting, it tends to slow it down. So So that's eddy braking, and one more example of Faraday's law.
Non-destructive testing. Ultrasonic examination. The basic principle of ultrasonic testing of materials is the propagation and reflection of sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section through the cylinder shows the position of the atoms, extremely magnified and simplified as a single crystal. To begin with, a rigid unyielding stop is attached to the right front end of the cylinder. At the left front end, a disc is installed. It will be used to transmit and receive sound waves. Pushing and pulling briefly at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which now serves as a receiver. A free end is also able to reflect a wave. In this case, however, the tensile side runs ahead in the reflected wave and finally deflects the receiver to the right. The reflected wave is even reflected again and actually travels for several times across the length of the cylinder, but this is not shown in the animation for the sake of simplicity. So, if a sound wave is generated at one end of a workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. For ultrasonic testing of a workpiece, not a large transmitter is used in most cases, but a rather compact one, which generates a short ultrasonic pulse. At a place free from defects, the ultrasonic pulse travels to the right front end, also termed back wall. The pulse is reflected and recorded again as an echo. When the transmitter is moved a little downwards, the cavity reflects a part of the wave. That part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse. For material testing, either the echo of a defect can be utilized, this is the pulse echo mode, or the phenomenon that hardly any sound waves pass through the imperfection. This is called the through transmission mode. In pulse echo mode, a transducer installed in a probe performs both the sending and the receiving of the ultrasonic pulse. On a computer monitor, the intensity is being plotted upwards on the y-axis and the time towards the right on the x-axis. With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse. In our laboratory, there's a green painted steel cylinder to be found. It contains artificial defects which are invisible from the outside. To track down the defects, the material tester uses the pulse echo method. This is how a typical probe looks like. Under the bright wear plate, a piezoelectric disc is installed. It can transmit and receive ultrasonic pulses. A computer operates the probe via a plug-in card and power electronics. On the monitor, the intensity is plotted upwards and the time is plotted to the right. After placing the probe on top of the cylinder, initially no echo at all may be seen on the monitor. The reason for this is the too small contact area between the probe and the workpiece. Only with the use of a gel, the so-called couplant, the ultrasonic pulses can get into the workpiece and can also go back into the probe. Now the back wall echo turns up on the monitor. The material tester spreads out the gel evenly on the top surface. That way she is able to examine the entire cylinder. Using the velocity of sound in the material, one can plot the calculated depth on the monitor to the right instead of time. A very useful feature. With the help of so-called trigger gates, which may be set on the echoes with a computer mouse, the depth of the defects can easily be read off at the lower left-hand corner of the monitor. The cylinder back wall lies in a depth of about 200 mm below the probe, so the cylinder has a height of 200 mm. And here we go. The The material tester scans the upper front end of the cylinder with a probe and observes the monitor. A defect echo appears on the monitor. This defect is located in a depth of 130 mm below the surface. Another echo indicates a defect in a depth of 87 mm. A second smaller echo at 174 mm is caused by double reflection on the same imperfection. And these are the defects. A drill hole and a saw cut. Filled up near the surface and painted, they are not visible from the outside. The drill hole in a depth of 130 mm. The saw cut 87 mm below the surface. Trams are popular means of transport in Karlsruhe in southern Germany. The tram cars are not only cleaned regularly, but also tested thoroughly in regular intervals by the transport company. Among many other maintenance points, the ultrasonic examination of the wheel axles plays an important role. A tram enters the maintenance hall for inspection. Some of the tram cars have already been lifted up. That way the bogies can easily be detached, pushed forward and examined carefully. This is one of the bogies jacked up to comfortable working height and prepared for ultrasonic inspection. Special attention is given to the wheel axle, among experts known as wheel set axle. It has been designed as a hollow axle. This saves weight and facilitates the ultrasonic examination. The material tester applies a suitable oil as a couplant into the bore of the axle. Now he takes a special probe designed exactly for this purpose, inserts it carefully into the bore with a mount, and evenly spreads out the couplants by turning and pushing. He has accurately marked the most important examination points at the mount. In an experienced manner, he positions the probe at the appropriate places within the wheel set axle and watches the monitor closely. The probe has specially been designed for this application. It transmits the ultrasonic pulses at an angle of 45 degrees. At a place without defects, no defect echo returns. But when the pulse encounters a crack which has grown in from the outside, double reflection occurs and a typical defect echo is recorded. It is important to note that also the shape of the wheel set axle may lead to an echo, for example at shoulders. These are so-called contour echoes. In this particular case, only contour echoes are recorded. No abnormality has been detected. The wheel set axle is perfect and can be used again to transport many passengers until the next examination becomes due.
Radiography testing utilizes ionizing radiation to achieve an image of an object on several different viewing medias. This may be gamma rays, or as in this case, X-rays. The examiner marks the weld to be inspected with a measuring tape. This will be visible on the X-ray. Thus, he will know how to determine the exact location of possible irregularities. The film is mounted on the object, and the X-ray tube is set up carefully. The examiner leaves the area, closes the lead door, and operates the device remotely. This way, he avoids coming into contact with the radiation. He adjusts the voltage, current, and duration, depending on the investigated material and the wall thickness. Then he starts the irradiation. The X-rays go through the material and generate a radiographic image on the film or imaging plate once processed. The experienced eye of the examiner interprets the image, and he can now determine the quality of the inspected object and if it meets the standards. X-rays can also be used to establish the authenticity of paintings, for example. Through the centuries, paint contained different quantities of lead. By exposing the paint layers to X-rays, it is possible to establish whether a cloth was repainted and the period from which the paint layers originated. In this case, the radiographic image is recorded on an imaging plate. Using the computer, a digital radiographic image is read. Art experts can use this to determine the authenticity of the painting.